All right, and just a couple of more topics having to do with heats of reaction to finish up this chapter. So Hess's law. So many reactions have been measured to find out what their enthalpies are, and they've been tabulated. And we'll find out at the end of this PowerPoint that actually there's another way that you can look up values and calculate the enthalpies, but one way of calculating enthalpies is to use Hess's law. So what is Hess's law? If a reaction is carried out in one step, or if the same reaction is carried out in multiple steps, it turns out that the delta H for the overall reaction should be the same as the sum of the enthalpies for each step. So, if you do a reaction in 3 steps and you add the enthalpies of each step together, it should equal the enthalpy of the overall reaction. So this is called Hess's law of Hess's law of heat summation. So basically it says that a chemical equation that can be written as the sum of 2 or more steps, then we can add enthalpy changes for each step together to get the overall enthalpy change. So here's kind of a diagram showing what I'm talking about. So if we start with our reactants, which are 2 moles of carbon, graphite, and 2 moles of oxygen, and what we're trying to do is form products, 2 moles of carbon monoxide and 1 mole of oxygen, there's a couple of ways we can do it. If we go straight, which they're showing you as step 3, is negative 221 kilojoules. But let's say we already knew the delta H for taking 2 moles of graphite and 2 moles of oxygen and making 2 moles of carbon dioxide. And then we also knew the delta H for going from 2 moles of carbon dioxide to 2 moles of carbon monoxide plus 1 mole of oxygen, and that was 566. So you can see that if you add together the 1, negative 787, plus 2, plus 566, you get the same as step 3. So this reaction, and you can see if you add the reactions together. So I've got it here, but let me write it up here. 2 moles of carbon plus 2 moles of oxygen. And the first step is going to 2 moles of CO2. Running out of room. And then if I take my second step, 2 moles of CO2, to give me 2 moles of CO plus 1 mole of O2. Now, if I add these reactions together, the 2 moles of CO2 will cancel, and I'll have 2 moles of C plus 2 moles of O2 to give me 2 moles of CO plus 1 mole of O2, which is the reaction I'm looking for. So if we take the delta H for this reaction, reaction 1, plus the delta H for the second reaction, reaction 2, we get the overall delta H. The delta H for the overall reaction that we're looking for, it's the sum of the other 2. All right, so let's do another example. Suppose you're given this data. So S solid plus O2 gives me SO2, negative 297 kilojoules, and then SO3 to give me 2 SO2 and O2 is 198. But what I really want to know is what's the delta H for this reaction? 2S plus 3O2 to give me 2 SO2. So what we need to do is we need to manipulate these equations to get them to add up to this equation. And I will tell you that if you're given these type of problems, they are meant to work out. So, you just kind of have to go step by step. A couple of recommendations that I have is I like to just zone in on one reactant or one product, one item at a time. So let me zone in on 2S. In the reaction that I'm looking for, I want 2S, and I want it on the reactant side. So I go up here and I look at my two equations, and I notice that S in the first equation is already on the reactant side. However, there's only one of them. So what I want to do is get 2. So what do I do to this equation to get 2S? I have to multiply it by 2. Well, if I multiply this by 2, I have to multiply each thing by 2. And if I multiply everything by 2, what happens to delta H? I also have to multiply it by 2. So that would be negative 594 kilojoules. Okay, so notice now that I've got 2S on the reactant side, and that's one thing that I'm trying to get in my overall equation. So that's good. And hopefully some things will cancel out, and hopefully we can get it to add this. So I'm not going to focus on the O2 yet because I've got it in both equations. So I'll try to focus on things that are only in one equation to start with and hope that the others will work out where they're meant to. All right, so now if I focus, let me change my color here. Now if I focus on, let's do purple. If I focus on 2SO3, I want that to be on the product side. All right, now I notice if I look at equation 2, SO3 is in that equation, and there's a 2 in front of it, which is what I'm looking for. However, notice that in this equation, it's on the reactant side. So what I want to do is I want to reverse it. So I'm going to write this backwards, 2SO2 plus O2 to give me 2SO3. And if you remember from earlier, what do we do if we, of course the others come along with it, but I'm just kind of being sloppy here. If I reverse the equation, what happens to the delta H? Well, the delta H changes sign. So the delta H for my new equation that I just wrote is negative 198. Now, if I add them together, notice what happens. I've got 2S. So I'll go back to my blue. I've got 2S on the left. I actually have 2O plus one more O, so I have 3O. Let's try a different color. 3O on the left. So S plus 2O plus another O. I also have an SO2 on the left, which doesn't show up here. But now if I look, I'll go back with my purple, SO3, so I have 2 SO3 on the right, and I have 2 SO2 on the right and 2 SO2 on the left, and so they will end up canceling. If I wrote the whole thing out, you'd see I could put like 2 SO2 here and 2 SO2 here, so of course they will cancel out. So what's the delta H? Since I added this reaction 1 with it multiplied by 2. So I did this reaction, and then the second reaction, which is this one here where I reversed it. So the first reaction plus the second reaction, so that's delta negative 198, gives me the overall reaction that I'm looking for. So that means delta H equals negative 594 plus a negative 198, which is 792 negative kilojoules. So these kind of problems, what you want to do is rearrange, and we know how to manipulate. If we manipulate an equation, we know how to change delta H. I think I go through this on the next few slides, so I'll just kind of repeat myself. All right, so yeah, we take the first equation and we multiply it by 2. So that's what I did here. And if you multiply the equation by 2, you have to multiply delta H by 2. Now we reverse the second equation, but we didn't have to multiply by anything because we already had our 2 SO3 on the right hand side. So we reverse the sign. Now, like I said, when we add them together, 2S plus 2O2 plus one more O2 gives me 3O2, and then 2SO3 on the right, and the SO2s cancel out. So negative 792 kilojoules. So again, remember, if you reverse a reaction, you change the sign. If you multiply a reaction by some factor, which could include dividing. So if you're dividing by 2, that means you're multiplying by 1/2. If you multiply by some factor, then you have to multiply delta H by the same factor. All right, so let's do another quick example. Let's determine the delta H for the decomposition of NaCl according to this reaction. 2 NaCl to give me N2, 1 N2 plus 1 O2 plus 1 Cl2. So given this data, so let's number these 1 and 2. Let's do another color. All right. Again, there's more than one way to start. I'm going to start by trying to get 2 NaCl on the reactant side. So I noticed that and again, like I said earlier, now in this case, I don't think there's anything that shows up in, well, except the NO, which hopefully will cancel because that's what we're trying to do here. This one looks a little simpler. Okay, so if I reverse, I get the NaCl on the left, and I want to double it, so let's write it here. 2 NaCl gives me 2 NO plus 1/2 times 2 is Cl, and I want to double my delta H, so negative 38.6. I reversed it, and I multiplied by 2. So this becomes 77.2 kilojoules positive. All right, and now, so we were able to not only did we get the 2 NaCl in place, we also got the Cl2 in place, so that's good. And now we want to get the N2 and O2 in place. Both of them are on the left, so I need them on the right, and I also need to double them. And so I'm going to do the same thing here. I'm going to reverse and double the first equation. So, and since I double them, I get 2 NO, gives me N2 plus O2. And of course, the gases all come along. I'm just doing this simply. And again, I change the sign. 90.3 times 2 gives me negative 180.6 kilojoules. So now we can see that if we add these two together, the let's get a different color here. The NO2s cancel, and I have 2 NaCl gives me N2 plus O2 plus Cl2. And so because I can add these two equations to get what I'm looking for, I can add these two delta H's together. Can't find my, there we go, can't find this. So negative 180.6 plus 77.2 gives me a negative 103.4 kilojoules. Okay, so again, I did that for you. I think this next slide will show you the process again. Okay, so there we go. I reversed both, this time I just did it this way. I reversed both reactions, so their signs changed. Then I doubled them both. So 77.2, negative 180.6. Now I add them all together. Notice that my NO2s cancel. And so there's my overall reaction, and my delta H is going to be the delta H of the first equation plus the delta H of the second equation, so it's negative 103.4 kilojoules. So these problems aren't too bad. They're made to work out. So like I said, sometimes it's overwhelming to look at the whole thing, but if you just go step by step and get one thing in place, then get another thing in place, either some of them will add together or they will cancel out. So. All right, but actually, so now that I told you all that, and there's likely to be a problem like that on the test, but actually there's an easier way of finding the delta H for a reaction, and that's by using standard enthalpies of formation. So let's start with the term standard state. standard state, of course, we could find delta H's for all kinds of reactions at all kinds of conditions. But in order to tabulate it, you kind of want to have some restrictions and make it a little bit more usable. So when we say standard state, it refers to the conditions chosen when putting them into this table or data. So a standard state means that we're at 1 atmosphere pressure and the temperature is usually 25 degrees Celsius. So we'll call standard temperature 25 degrees Celsius or 298 Kelvin and 1 atmosphere pressure. So then by using Hess's law and compiling lots and lots and lots of reactions, we're able to determine something called the enthalpy change for a reaction in their standard state, and we denote it delta H naught or delta H 0. So that's indicating the little 0 just means standard state. And then, like I said, after taking lots of different reactions and analyzing them, we're able to tabulate the delta H naught sub F, which stands for the standard enthalpy of formation. So in other words, it is how much energy it takes to make the compound in question from 1 mole of the compound in question from the component elements in their standard state. So let me say that again. Let's see if we have an example here. All right, so let's just say, let's give an example. So let's say we're trying to find out what is the delta H of CO2 gas. We want the delta H of formation at standard state. Well, the standard state just means 1 atmosphere and 25 degrees Celsius. So basically, we want to know how much energy does it take to make carbon dioxide from its elements. So if we take carbon and oxygen and form CO2, what's the delta H? These numbers are tabulated in a chart in your book, and I think on the next slide. Do note that the standard enthalpy of formation for any element will then just be 0, because, you know, if you're trying to say how much energy, what's delta H to make carbon from carbon, it's 0 because it's already carbon. So same thing, how much enthalpy does it take to make pure oxygen from pure oxygen? Well, of course, there's 0. So if you have a pure element, the delta H of formation will just be 0. The good news is that if you forget that and you look it up in the chart, it will tell you it's 0. So that makes it handy. So like I said, you'll find these delta H formation tabulations. Many uses. So if we know all the delta H of formation for all reactants and products by Hess's law, but we'll do it much simpler than that, we can actually determine the delta H for any reaction at standard state. So it does use Hess's law, but it's actually going to be much easier than manipulating the equation. It's kind of like it's already been done for you. So here's an example of the table. This is actually not from your textbook, but from a different textbook that I have, that I had the picture of handy. But and just note that sometimes values are maybe slightly different between textbooks, so just use the ones you're given. Notice that if you have an element, so like here we have calcium. Calcium is an element, and so to make calcium from its element, it's 0. Same thing with here, carbon, graphite. Although to make a diamond, there is a delta H. So if it's other than its standard state, there's a value. But if it's its standard state and it's elemental, it'll be 0. But like I said, it just tells you that, so you don't have to worry. If you are working some problems, for example, if there's a test, I will give you the data that you need on the test. If you're working any homework problems and they're not given to you, just note that either you can use this slide, although this is just a subset of the bigger, it's like 3 pages, I think. If you look in Appendix G of your textbook, you'll find other values. So if you're working a problem in active or something like that, and you don't see the values given, and it's one of these types of problems, then they're assuming that you're going to look them up in the appendix. And like I said, values will be given to you on a test. So here's the equation. So this is called the law of summation of heats of formation. So this says that I can find the delta H for any reaction if I take the sum. This is the symbol for sum. I sum up all the delta H of formations for all the products. The little n is the coefficient. So I take the delta HF for all my products times their coefficients, sum them up, take all the delta H of formations for all my reactants times their coefficients, sum them up, and then take the sum of the products minus the sum of the reactants, and that will give me the delta H for the overall reaction. So again, sigma is the mathematical symbol meaning sum of, and M and N are coefficients. But let me just do an example for you. All right, so nitroglycerin is a powerful explosive that forms 4 different gases when detonated. So here's my reaction. And it says, what is the delta H for this reaction? Use Appendix G for most of your data. If you look up in Appendix G, you probably won't see nitroglycerin, so they're giving you that value. The value for the delta H of formation for nitroglycerin is negative 364 kilojoules per mole. I think I have the values. Do be careful, especially with water, because water, of course, can exist in a gaseous state or a liquid state, and the values are different for water, liquid, or gas. CO2 is pretty much standard because it's almost always a gas. So, so I'm going to go ahead and look up. You can go back to the previous slide and look at it. I do know that oxygen is pure, so I already know that's a 0, that's a 0. But I have to look up H2O and CO2. I can't go backwards when I'm recording, so let's go forward. Okay, so let's do it. So that you want to start out with the products, and you want to multiply by the coefficient. So we're summing them all up. So we've got 1/2 times 0. I'm going to go ahead and make zeros with the little line so we know the difference between that and an oxygen. 3 times 0. Of course, you don't have to do that, but I'm just trying to be as careful as possible. 5 times negative 241.8 plus 6 times negative 393.5. Do be careful with your signs. All right, so that's obviously 0 plus negative 1209 plus negative 2361, which is negative 3570. And then I subtract, so that's all my products. I subtract all my reactants. In this case, there's only 1. But do be careful with your negative charges because it's minus this quantity, and the quantity is 2 times negative 364. So we have, which is negative 728. So we have negative 3570 minus a negative 728, which is obviously plus, so that gives me negative 2,840 kilojoules. So I think I worked through this on the next slide as well, so I'll go through it again and there, and I think I have some more words that'll pop up and get mixed up. But okay, so you can calculate delta H by multiplying the values by the coefficients in the equation and then subtracting reactants from the products minus reactants. All right. Okay, so yeah, I've got it here. So we sum up all the products, multiply by their coefficients, sum up all the reactants multiplied by their coefficient. So the products, like I just did, shows you. So 1/2 times 0 plus 3 times 0 plus 5 times negative 241.8 plus 6 times negative 393.5, negative 1209 plus negative 2361 is negative 3570. My reactants, 2 times negative 364 or negative 728. So negative 3570 minus a negative 728 gives me 2840 kilojoules. Don't forget to put your units at the end, and also, as this says, be really careful of arithmetic signs. Negative signs, they're often a source of mistakes. So you know what you're doing, but you're just a little sloppy or quick or something, and easy to make mistakes. So do make sure to show all your work when you work these problems so that I can see where you went wrong and can give you partial credit. All right, so let's look at one more example. Calculate the heat of combustion of 1 mole of propane gas in oxygen. And here's our equation. And again, be careful to look at the phases because this time water is a liquid that we're looking for. So I'm going to look up on the table in Appendix G the values. So C3H8, negative 103.8. Oxygen, of course, is 0. CO2, just like the last question, is negative 393.5, and for H2O liquid is negative 285.8. So I take my products, 3 times negative 393.5 plus 4 times negative 285.8. Sum that up, which is your negative 1180.5 plus a negative 1143.2. Both of my reactants, 1 times negative 103.8 plus 5 times 0, which of course is negative 103.8. So if I take the products minus reactants, I get negative 2219 kilojoules. Again, note that water in this reaction is liquid, so make sure to look up the proper value. So that is the end of chapter 5, heats of reaction. What should you be able to do in this after learning this chapter? You should be able to calculate kinetic energy, define kinetic energy for that matter, just heat of motion, or kinetic energy, energy of motion. Be able to write thermochemical equations, knowing if they're exothermic, endothermic. Manipulating thermochemical equations, so like we did with Hess's law, if you reverse them, you change the sign. If you multiply by some number, you multiply delta H by that same number. Be able to calculate the heat of reaction from the stoichiometry. So like earlier problems we did in this PowerPoint presentation. Be able to relate heat and specific heat, so be able to do calorimetry type problems with specific heat. Calculating delta H from calorimetric data, again, so calorimetry, be able to use Hess's law to find delta H if you're given a couple of other equations, and then of course being able to calculate delta H for a reaction from standard enthalpies of formation, delta H sub F at standard temperature and pressure. And that's it. Thanks.